Okay, since I got involved with line following robots, I've been using Pololu. I'm not quite sure how you say that word, but I'll carry on pronouncing it like that. Pololu line sensor arrays rather than the more traditional pair of sensors. And just going to give a short presentation now on why I'm doing that and how I use them. So first I go through quick background on why I'm doing it, talk about the benefits of using an array rather than a pair, show some of the different types of reflectance sensor arrays available from Pololu, and also say a few words about their digital reflectance sensors, which are a little bit different to what I think most people are using. And then show how easy it is to program for line following using the Pololu libraries. Okay, I got involved with line followers shortly after I retired when I visited TechFest back in July 2013. I wanted to get involved, and it looked like line followers were probably the easiest way to do it. So I thought I'd build a robot for RoboFest later that year, and failed spectacularly. 2 weeks before the event, I had nothing that would run around a simple track. So I bought an off-the-shelf solution, a Pololu 3Pi robot, and took that along to see how it went. Here's a picture of the underneath of that robot. And if you look carefully, there are 5 sensors around the forward edge of the robot, forming the array of sensors that this uses. It worked, and I decided to use the same approach when the first IET triathlon came along in early 2014. So for that robot, I built one using a Pololu array sensor, and it worked quite well. Here you see at the front of the robot an array of sensors and 2 single sensors for detecting the start-finish line. Quite why they're both on the same side made sense at the time, makes less sense now, but never mind. And I carried on using these sensor arrays because they worked well. And all my subsequent line follower robots have used a similar array. Here's the UK Mars bot I'm putting together. Again, it's using an array of 6 sensors at the front and individual sensors for line and curve detect. Start, finish, line, and curve detect sensing. So, I mean, why use an array rather than a pair? The principle is very similar, but a sensor pair is simple to implement. It only uses 2 analog channels. It comprises 1 central or maybe 2 individual LED emitters and a pair of phototransistor detectors. You shine the emitter downwards, measure the reflectance values seen by each detector, and then you calculate the line position and the error of the robot from the center of the line. Straightforward. Why do anything different? Well, a limitation of this method is that you can only separate the 2 line sensors so far before the actual center of the line becomes quite imprecise. I use the word linear very loosely here, but if you're trying to get some kind of linear-like error measurement, you don't want it getting fuzzy at the central point. So if you use an array instead, you can have each sensor pair, if you like, each pair of sensors fairly close together, giving you a relatively linear error measurement in between that pair of sensors, and then just extend to a length as long as you like, giving you the ability to recover from quite significant errors. And as you see, it's still pretty simple to use, but the obvious downside is you're using more I/O channels on the microcontroller. So, what kind of sensor arrays do Pololu provide? Well, this is the standard array. They do two types. These red ones are the old traditional Pololu sensors. They've since started replacing them with a new type, which I'll show next. But concentrating on the old types first, I still use these. I've got several of these in my bits box, and they are still available. It's got an array of 8 emitter and phototransistor pairs. It's using UV emitters, and you've got one pin which will turn on or off all the emitters on the array. The pitch is actually 3/8 of an inch, which is near enough 9.5 millimeters. And if you don't want 8 sensors, you can break off the last 2 and have a 6 sensor array and a separate 2 sensor array. And there's also a single width unit, which you can use for side sensors. The new types, they've actually got a much wider variety. I don't like them because they have the sensor is wider and occupies more space for the same length of sensor. So I'm less keen on these, but eventually if they move to them completely, I'll have to use them. You can have a sensor width of 1 up to 31 pairs of emitters and phototransistors. And they're available in 2 pitches, either 4 millimeter or 8 millimeter sensors. More flexible in that you can firstly switch each pair of emitters on, so you can break down the sensor, the total array, into pairs of sensor and switch the emitters for each pair individually. And you can set the emitter brightness. There's a way of dimming the emitter so that you're using less current. They also make a thing which they term a digital reflectance sensor. And the ones I used early on were all digital reflectance sensors. The 3Pi uses them, and my IET triathlon robot used their digital sensors. They look almost identical to the analog sensors, but they have an RC network on the sensor output. And the way that they're used is the emitter is briefly pulsed, and then the internal timer on the microcontroller measures the output decay time. A high reflectance, such as the white line, will give a short decay time, and the black area will take longer to decay. You only need to use a digital input pin on the microcontroller. You don't need to use analog pins. And one sensor measurement will actually measure all the sensor outputs in parallel. Like all things, there's a trade-off. To measure 8 sensors, the default measurement time is 2 milliseconds. This is the default timeout for the sensor measurement. If you're able to handle less dynamic range in the black-white difference, then you can lower the timeout to fractions of a millisecond. At some point, I'll look and do some detailed testing on how much it's worth lowering this default measurement time. but I've not done that yet. I've tended to default to 1 millisecond measurement time for all the sensors. The principle of using the sensor array is pretty much the same as just using two sensors. You calibrate the black and white reflectance levels. You generate a normalized sensor reading. I use 0 for black. Actually, I'm not sure I've got this the right way around off the top of my head, but 0 in 1,000 for black and white. And then calculate the offset of the sensor array from the line sensor and use a proportional differential control loop to correct the position error using the motors. Pololu provide two libraries for using their reflectance sensor arrays. And you can use the same library both for their analog and their digital sensor arrays. They've got one older library written for C and C++, and that's what I used to use when I was doing this 7 or 8 years ago. And then more recently, they've produced an Arduino library for the same sensors, which you can use together with Visual Studio Code and Platform IO. And yet there are functions to calibrate the sensor black and white levels. So you start the calibration, in some way move the sensor around, either manually or get the robot to rotate, which is what I do. And it will generate two arrays with a value from maximum, two arrays, one array for maximum values for each sensor and another for minimum reflectance level. And you can generate a total of 4 arrays, 2 with emitters on, 2 with emitters off. There's a function to read all the sensor values into an array, again, with emitter on or off. And then you can read out the sensor values, either raw sensor values or normalized sensor values, recalibrated using the reflectance levels. And then a very useful function which will use the information in the sensor arrays to generate a single number, which is the line position. And so if we have an array of 6 sensors, the total value range of that single number is between 0 and 5,000, with 2,500 obviously being the central line position. And the way that the function works is it weights each normalized sensor value by multiplying by the sensor number from 0 to 5 in this case. And then the line position value equals the sum of the weighted values divided by the sum of the unweighted values. I saw an explanation of this separately from the Pololu library. I was looking through everything I could find on Micromouse and saw Peter's article on his website, which he wrote in 2011 for his Micromouse robot Bob. And I'd be interested, once I've finished, which is very shortly, in whether Peter actually ever used that algorithm and how he found it. The result isn't, as Peter says, it's not perfectly linear across that range, 0 to 5,000, but it is monotonic in that as the error increases and decreases, so does the value. Pololu have also added some code to the function to constrain the position value between these min and max values, such that if you go further to the left than the 0 value, then the value will stay at 0. And if you go further to the right, maximum will stay at 5,000, such that if you have a very large position error, your robot should be able to still find the line. So that's it. They work for me, basically. I find that the reflectance sensor arrays are easy to use with the Pololu libraries, and they're incredibly effective, which is why I use them. Okay. Any questions?
Chris, thank you. Any questions for Chris? I've got a couple.
What do they cost?
That's a great question. I think I paid the last time I bought some not that long since, earlier this year. I found them on Amazon, the old style sensors, and I think I paid something like £8 to £10 for an 8 sensor array. So it's an expensive approach. It would probably not be a practical thing for school use. Do I need to turn this thing off?
No, you're okay.
I'm okay now. Okay.
Yeah, good.
It's probably not too practical for school use, but I don't find it an outrageous price for building a line following robot for me to play around with. I think their new ones are maybe a bit more expensive, but we're not talking anything greatly different from that figure of about 10 quid for a decent width sensor.
Okay. Can I ask a question here, Chris?
Yeah.
So your positioning of your sensor array would be centrally over the line. Is that where you're putting it?
Yes. It doesn't really matter whether you're using an odd or even number of sensors. It all comes out in maths.
Right. And so you have a normalized nominal value that would be the value if you were on the line, and then above that will indicate you're going one way over the line.
Absolutely.
And below that you're going against the other way. Yeah.
Yeah. The value is the number of sensors minus one. Oh, the maximum value is the number of sensors minus 1 times 1,000. So for 6 sensors, the range is 0 to 5,000.
And you'd be looking
the
for 2,500.
position is obviously 2,500.
Okay, thank you. Anybody else? Questions? Peter, did you want to pick up that question from Chris?
Yeah.
Oh, yeah. Did you ever try this, Peter?
Yeah. Oh, yeah. It's in, I've got a line following UK Mars bot, which uses just 4 sensors for the line, and it does exactly that.
Right, good.
And I've just put on the messages a link to the article, which I presume you mean. Looked like 2011 was a busy year for me. I have a lot of stuff there. And the only comment I would make is, no, 2 comments. One is, for it to work reliably, you need to have the sensor values normalized, as you've done, so that it will give the same peak value over the line. And the other is, where you've got your first sensor multiplied by 0, which still all works peculiarly, but it notionally throws away the information in that sensor. Instead of that, you put, for the one just to the left, you do minus 500, and the one just to the right, you do plus 500, and then, so it'll be plus 500, 1,500, 2,500. Right?
Well,
you're not throwing away any information.
Well, you're not throwing away the information because the information is still there in the unweighted number. And I would maintain it's exactly the same.
Well, perhaps we can discuss this then at some point other than now. But I'm more comfortable in doing the weightings from center 0 for 2 reasons. One is I know for it throw anything away because they all contribute to the sum, and the other is you automatically get a positive and negative number just to the offset.
Yeah,
so you're saving you an addition, but it's.
I had similar reservations at first. I mean, I thought about it and decided that you were really just shifting the numbers, and it was the same method, is the conclusion I came to. But I didn't think about it incredibly deeply. So I wouldn't argue the point too strongly.
Right. Okay, anybody else, any questions?
Okay. I'll point something out. It's an interesting difference, and that method I've seen used in really old Micromouse that used to have an array of sensors like that above the top of the wall. So essentially, they were using the method to follow on the top of the wall. They'd have one on either side, and that's so could swap between the two. But yeah, it's the same. It's the same way that a lot of the older mice used to sense the walls.
Not that I wasn't paying attention, mind, but I was just trying to remember why it was that the weighted line follower sensor value technique appears to work even though you divide by zero, even though you have a multiplier of 0. And it's because the method as originally described uses the sum of the raw unweighted sensor values as a divisor to normalize the answer, right? And so that value isn't thrown away, it's still included in the calculation. Nonetheless, you get a more, to my mind, tidy answer if you have positive and negative weights. But it was bugging me that I couldn't work out why that multiplier by 0 didn't do anything, and that's why I've just done the sums.